get this up on the screen. Here you go, just to get you started this morning. Let me get your chat fingers working. Which balloon do you feel like today? At this bright and early time of a Tuesday morning. It's a Monday Tuesday though, right? Because it's our first day of the week, so it's Monday, but it's a Tuesday. It's a Monday Tuesday. Well, we're kind of all over the board. Let's see. 6, 1, 5, 4, 2, 3. Oh, no 3. Several 4s. Okay, 4's okay. Got a lot of 1s. It's just totally deflated. We got some 1s in here. Got a few 1s. Got a 5. But autumn's at 6. All inflated, sparkly, ready for anything. I'm kind of a 5 myself, I think, this morning. I'm inflated. I feel rested. I feel good. I just got a lot to do. I don't feel like sparkling at this point. I don't know that I got that in me. But 5's okay. 4's okay. I mean, you're getting there, But these 1s, I tell you, well, we got to work on these 1s. That balloon doesn't even look like it could be blown up. It looks like it was. It's tied, so it's already burst. It's already burst. Need to at least get those 1s to a 2 where you can be inflated again. But yep. All right, we see all that good stuff. Okay, well, we got most everybody in here. Let's take a look at what we have this week. So in Buzz, looking at our 0B class, if we go to the grade screen, we had that one assignment last week, arithmetic sequences. And this week, we got 2 assignments. We're going to look at arithmetic series, which you have to imagine would be similar to arithmetic sequences. And then we're going to look at geometric sequences. And then we'll look at geometric series next week. We bump that back a little bit. So I think I may take 5.06 out. I'm not sure on that one. I have to look at that. Arithmetic series, geometric sequences. That's what we're doing this week. I got to get that put into Google Classroom too. But let's look and see what arithmetic series means. What's the difference between that and a sequence? Because we've seen arithmetic sequences last week. Well, here we go. So let me do a little story to start us out here. So upon opening your first savings account, you make an additional deposit of $25. I think when I opened my first savings account, I was a little bitty. I was like 8 or something. I think I put like $37 in there. It was birthday money, it was something like that. So every month for the next 5 years, you increase your deposit by $15, not including interest. How much is it worth at the end of the years? Now it says increase your deposit. That means the next month we're depositing $40 because we deposited 25 and then we increased that to 40 and then we increased that to 55 the next month and then we increased it. So we must be getting some good money by the time we're 5 years in because that's adding a lot. So sequences wouldn't help you find out how much you would deposit in the account in 3, 17, 26, any of that. Because sequences is just the next number. But it'll help us find that because that's what we learned last week. How do we find the 26th number in a sequence? So we could calculate how much we would be deposited in month 26, but how much money would we have in there? That's what we need to know is, if we deposit all this money, how much do we have in our savings account now? So to figure that out, that's what the arithmetic series is. That's when we have a sequence and we just add all those numbers together. Add all those numbers together, arithmetic sequences. So let's take a look at arithmetic series. So yeah, it's very similar to a sequence. It's a list of numbers which share a common difference. So the list is going to look like a sequence. In fact, it is a sequence. But a series is adding that sequence up. So it's going to be separated by a plus sign rather than by commas. See, so here it is, like 4 plus 14 plus 24 plus 34. That would be a series. So we're supposed to drop this in there and which one's which. See, that's a series because we're adding all those together. So that'd be a series. Now, this one we saw last week, 3, negative 147, negative 297, negative 447. That's when we subtract 150 every time. Common difference. But that's a sequence. We're not adding those numbers. We're just finding the sequence. 1, 2, 3, 4, 5. Common difference of 1. We add 1 every time. That's a sequence. 10 plus 8 plus 6 plus 4 plus, there we go. That's a series because we're adding them together. So that's the difference between a sequence and a series. They all have a common difference. It's still arithmetic. It has a common difference where they're adding or subtracting the exact same number every time. But with a series, we're keeping a grand total. All right, so let's discover how to find the total without having to add each term to the next. So I'm going to change how I'm sharing this so that you can hear the audio, because it doesn't like it if I don't do it right. Here we go. Share it this way. And let's see what our video is going to tell us about this arithmetic series. Make that bigger on the screen. This is only 22 seconds here, guys. I don't know about you. I'm not hearing anything. I'm not sure there's any volume. Volume's up. So let's just see what they're doing here. So they're just doing, let's see, 4 plus 1 plus negative 2. I don't see where they got their negative 7 there. Oh, I need to go back to where they started at. What they start with? Now, that is a sequence they started. They're going down each 3 times, all right? Oh, so they're taking the first number and the last number. 4 plus negative 11 is negative 7. 1 plus negative 8 is negative 7. Negative 2 plus negative 5. So they went to the first term and the last term, and then the second term and the next to last term, and the third term and the third from last term, and add those together, and they get this negative 7 each time. Well, that's kind of interesting. So each pair of terms adds up to the same number, negative 7. So finding the sum would be pretty easy, because since we did that 3 times, negative 21 is what the total of all those numbers added together. So we could find some kind of formula that's going to work. So let's see what we have here. Oh, this is where we have to know our vocabulary. Let me make this bigger on the screen, because we're going to look at the terms. A sub n, A sub 1, n, and d. Right? This is the same terms we were using last week with the arithmetic sequences. So d, we know, is the common difference. The common difference. So just a good refresher of what our terms are. A sub 1, we know what A sub 1 is. That's the first term in the sequence, right? A sub n and n. We have the number of terms in a sequence and the last term in a finite sequence. Well, we know n would be the number of terms, and A sub n, like if n is 10, that means there's 10 terms, and A sub 10 would be the last term. All right, great job. We got that. All right, we can make that smaller again. All right, let's get into this on page 3. Then we'll hit our lesson somewhere around 4, so this isn't going to be quite bad. All right, now they want to find a formula for arithmetic series working backwards. Let me see what's going on with our volume on here, see if there's anything that would be causing a problem. Now we should have sound, if there is sound. See if there's sound this time.
The sum of the 6 terms of the arithmetic sequence is negative 21. Negative 21 can be rewritten as 3 times negative 7. 3 represents the number of pairs in the arithmetic series, and negative 7 is the result of negative 21 divided by 3. The 3 pairs in the arithmetic series can be written as 6 divided by 2, where 6 represents the number of terms in the series. Negative 7 can be written as 4 plus negative 11. 4 represents the first term of the series. And negative 11 represents the last number of the series.
Okay, so that's given us a good hint on how we come up with a formula to add an arithmetic sequence all the terms. So what they demonstrated back on the page before, in the other video that we saw, was if you take the first term and the last term and you add those together, and then you multiply that by the number of terms divided by 2, because you're cutting the terms in half when you add them together like that. So that gives us a formula. So I'm gonna switch and put that on our screen here. I'm gonna stop presenting this way. We're gonna write this in our notes. So I'm gonna put up my screen the other way now, just so I can put our notes up there. All right, so when we put in our notes, S sub n. All right, S, that's for sum. When you add numbers together, you get a sum. So the sum of all the terms, we take the total number of terms. How many terms are there in our sequence? We'll divide it by 2, and we'll multiply that by the first term added to the last term. Oh, not n squared or n sub 2. It's a sub n. All right, so arithmetic. Oh, no H in back. Arithmetic. See, my brain's. That's why I'm not sparkly this morning. Arithmetic series formula right there. We have the first term and the last term, add them together and divide or multiply it times the number of terms divided by 2, which would be the same n, right? Because that's a sum. If we got 10 terms, we're going to take 5 and multiply it by the first plus last term, add it together. All right. So that's in our notes now. First term, last term, add together. Number of terms divided by 2. So when they had that 4 and the negative 11, they had these 6 terms in their sequence. When we took the 4 and the negative 11, that was negative 7. And there's 6 terms, so we multiply by 3, and that gives us the total. Now, you can add all those up and double check it. 4 plus 1 is 5, plus negative 2 is 3, plus negative 5 is negative 2, plus negative 8 is negative 10, plus negative 11 is negative 21. So that's correct. All right. So there's also another way we can come up with this, because maybe we don't know what the last term is. So if we look back to our sequence, if perhaps we don't know, maybe we just have the first term and the common difference, right? Or maybe we just have the first 3 terms or whatever, and we can calculate the common difference. And we say, okay, how much would the first 40 terms add up to? And you're like, well, I don't know, because for this formula, I have to know what the first term is and know what the last term is. So if I just add, let's just do one for example. 3, 6, 9. And we want to know what S sub 40 is. If I add the first 40 numbers together. Well, to use this formula, I can put in 40 as n. So n divided by 2, 20. 20 times the first term, which is 3, plus the 40th term. I don't have the 40th term. Remember, we had this explicit where if we have the first term, we can do n minus 1 times the common difference. Well, we can also take this and put this in our formula and come up with a new formula for when we don't know. So let's do that. S sub n equals n divided by 2 times a plus a sub 1, the first term, plus, but I don't know a sub n, but I know a formula for a sub n. So let's just substitute this in. We'll take that and substitute that in for it. A sub 1 plus n minus 1 times d. See, that's same thing right there. Just substituted it in. So now we can simplify this. So S sub n equals n divided by 2 times, we got a sub 1 plus a sub 1, so 2 times the first term. 2 times a sub 1 plus n minus 1 times d, or d in front of it if you want. We can put the d in front of it. But anyway, that's simplified down there. So we can take 2 times the first term. So on this one, so we can take n divided by 2, 40 divided by 2, times 2 times the first term. 2 times 3 is our first term, plus n minus 1. That would be 39 times the common difference. 3, 6, 9. So our common difference is 3. It's going up plus 3 each time. So let's see. Let's do some simplifying. So that's 20. That's 6. 39 times 3. Let's pull up our calculator to make sure we get that right. 39 times 3. 117. So this equals 20 times 123. Twenty times 123. So if we add up 3, 6, 9, 12, 15, 18, 21, all the way to the 40th term, that's going to equal 2,460. So we did that with this formula. See, we have two formulas now. We have a formula when we know the first and last term. Oh, let me get rid of that. Formula when we know the first and last term. And when we don't know the last term, we only know the number of terms. We know the first one, and we know how many there are. So 2 times the first one plus n minus 1 times d. And then multiply that by n divided by 2. So there's the two formulas you need for an arithmetic series. And then we already had our number, our arithmetic sequence. All right, so we had these last time. We had the recursive and the explicit. For a sequence to find a term, this is to find the sum. So right away we can tell whether we're doing a sequence or a series. Are we trying to find a sub 10, or are we trying to find the total of the first 10? S is sum. Let's put that in our notes. S equal sum. That is the total. All right. Let's go back and see what else they're saying. So there it is. 2 times the first term plus n minus 1 times the common difference. And then all of that is multiplied by n divided by 2. All right. So they took the same sequence that they had, those 6 terms, and they used this formula instead. And they still come up with negative 21, which you should. It still adds up to the same thing. But they just did 2 times the first term, and they did the number of terms minus 1 times the common difference, and you still get to the same place. Even though in this case, they know the 6th term, so they can do either formula. They're showing that it works. All right, and then there's the lesson summary. So that's it. We just added a series onto the sequences that we learned last time. So the main thing we said to learn is these two formulas, 2 different ways to calculate the total of adding a sequence together. So this was a lot quicker and easier than last week, because last week we were learning how to derive a sequence. Today we just learned how to add them all together. So it's not bad. So here's some practice. Here's some more examples on this page. But they do give you some practice as well. If you have a series with 23 terms that starts 5, 7, 9, and you were trying to find the sum of the first 23 terms, which formula would you use? Well, in this one, you don't know the 23rd term, so you would use the second formula, the 2 times the first term plus n minus 1 times d. And then you can find the series for that, the total. Here's an example for you. Find the sum of the arithmetic sequence that starts 11, 18, 25 when there's 31. So I'll let you do that on your own because I give you the answer in this video. So this is where it gives you lots of practice during the lesson before it counts. So you should go back and do these practice problems. Here on page 5, there are multiple practice problems for you to try. There's 4 on this part right here, 1 of 4. What is the sum of a 44-term arithmetic sequence where the first term is -9 and the last term, the 44th term, is 120? So you can use that first formula there because you know the first, you know the last. So you can use that and find that. And then after you solve that one, go to the next one. There's 4. And then there's activity number 2. And this will use the other formula, I would guess. What is the, this is a little different way. What is the first term of a 14-term sequence where the last term is -12 and the sum is 42? Oh, that's a good one. I like that. Maybe we should work that one together on paper just to practice that. So what's the first term? A sub 1 equals what? When we know that a sub 14 is -12, and we know the sum equals 42. Okay, let's work that one together just because they gave us a little twist here. We got to find a sub 1. We don't know a sub 1. We do know a sub 14. We do know the sum. So if we go to this first formula, okay, so we can say 42. Notice I'm substituting S sub n. What's the total? Well, I know what the total is. So I'm gonna substitute in there. N divided by 2. Well, we know they said the 14th term, so 14 divided by 2. We don't know what the a sub 1 is. That's what we're trying to find. But we do know a sub 14. We do know the last term plus -12. So just take a formula. If they give you a problem like this, take whichever formula is appropriate. Since they gave us the last term, they did not give us the common difference. So we could not use this formula. We don't have the D. We'd be looking for 2 different things. But we do know the last term and the N. So pick the formula you need and work backwards. So 42 equals 7 times A1 minus 12. Since it's plus a negative, we can say minus 12. So we have to distribute here. 42 equals 7 A1s. And then 7 times -12 is -84. Okay. Let's get A1 by itself. Add 84. 126 equals 7 A1s. Divide both sides by 7. So A1 equals, and we can pull up our calculator, make sure we got that right, but I think it's should be 18 now, right? 126 divided by 7, 18. So now we know the first term is 18. And that's the answer. So it starts at 18, it goes to -12. If you add them all together, you get 42. Like that. Put a little twist in there. All right, let's put it up. So we said it was 18. Submit. Excellent. Say, there we go. So you go check the next problem they got for you. What is the common difference? Oh, now they gave you the total, 2256, first term of -7. and they want to know what the common difference is. Well, if you look at our two formulas, this one ain't going to tell you a common difference because it doesn't use the common difference anywhere. So you should substitute into this one, because you have the first term and you know how many terms there are. So you know what n is. N is used all over the place. And you know what the total is. So you know the total, you know the n, you know the first term. You just don't know the d. So you can substitute that in here and solve that one. All right. Let's go to the next. Let's go look at the assignment actually for this. Again, you have 3 attempts. So if you don't do well the first time. By the way, if you don't do well the first time, let me leave here. You can hit grade details when you actually have a grade. And you can look at your questions there if you want to see what you got wrong, because you do need to be able to do that, right? So let's look at this. The first and last terms of a 10-term series are listed on the table. So the first term is 3. The 10th term is 75. What is the sum? So that just uses that first formula. Identify the 33rd term when they give you the first term, the second term, and the third term. Okay, so you should be able to use a formula for that. Mike started a savings account by depositing $9. Every month he deposits more than the month before. And at the end of 41 months, he has saved over $9,000. How much more does he deposit each month? So he's depositing the same amount more every month. How much is that how much is that common difference? How much is it going up per month for his deposit? Let's see what I got. 5 questions. Each level of a smartphone app adds more gems for you to match. Level 1, you got to match 13 gems. On level 12, there's 123 gems. When you complete all 12 levels, how many total gems will you have matched? Okay, so they give you a sub 1. They give you a sub 12. You have a formula for that. The seats at a local baseball stadium arranged so each row has 5 more seats than the row in front of it. If there's only 4 seats in the first row, how many total seats, how many total tickets can you sell if you have 24 rows? All right, so there you go. 5 simple questions that you have the formulas for. 5 questions. Let's look at geometric and see how this compares now. So we're going to switch gears from arithmetic to geometric. All right, so they're going to show us some sequences, and we have to identify the pattern and do the next 3. So I'm going to put this for the chat right here. I'm going to make this bigger where everybody can see it. There we go. All right. 1, 4, 16. What are the next 3 numbers? I know I'm going to need a calculator on this. Maybe. You might be able to do the next one in your head. Maybe able to do all in your head if you're a human calculator. That'd be wonderful. All right, let's see how you're doing there, guys. 1, 4, 16. What's happening between each number? It's obviously not arithmetic because it adds 3, then it adds 12. So that's not consistent. It's not arithmetic. Something else is going on. Mackenzie's already on top of it. She says it's just multiplying by 4. 1 times 4 is 4. 4 times 4 is 16. 16 times 4 is 64. Here, we'll type that in. Kellen says, yep, that's absolutely right. So it's Laura. She's with it. 64 times 4 is 256. And 256 times 4 is 1,024. So submit that. See how we're doing. Excellent. See what else they have for us. 2. Let's do this one too. 2, -6, 18. You're like, what? Is that multiplying by the same thing each time? It's not adding the same thing each time because it adds -8 and then it adds a positive 24. So that's not. This is actually a geometric sequence. It is multiplying by the same number each time. 2 times what number is negative 6? And then you can multiply negative 6 by that same number and get positive 18. Little tricky, but don't let that fool you. Geometric sequences can alternate. Positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. When it's multiplying by a negative number. 2 times negative 3 is negative 6, right? 2 times negative 3, because 2 times 3 is 6, and it changes to a negative. And then you multiply negative 6 times negative 3. When you have a negative times a negative, it turns back into a positive. Mackenzie's on this one too. So 18 times negative 3 is negative 54. 18 times negative 3. Negative 54 times a negative, that's going to be a positive number again. 162. Let's see if this is right. See if Mackenzie's got these numbers. 162 times 3 is 486, but it's a negative, so now it's negative 486. Up, Laura, see what she did. So it's multiplying by negative 3 each time. So this is going to alternate. Positive, negative, positive, negative, positive, negative. The next number would be a positive. Let's submit and see if we're right. Yes. Multiply by a negative, and it will alternate. We'll look at the next one. This one just does fractions. One, I don't know why there's a dollar sign on both sides of the number. That's weird. 1, 1/2, 1/4. So it's obviously multiplying by 1/2 each time. So 1 times a half is a half times a half is a fourth, fourth times a half is an eighth, eighth times a half is a 16. So we'll bow out there. Let you guys, if you want to go back and see if you can get those last two. This is 3 of 4. So just look at page 2 though. Let's move on. That just helps us recognize what a geometric sequence is. So this is a list of numbers called terms that share a common ratio. See, this is not a common difference. The difference is when you subtract two numbers. But with a geometric sequence, it's a common ratio. We use an R, right? Because you're multiplying by the same number. So a ratio is when you divide. Oh, that's a good time for an example here. All right, we're going to put this up on our screen. So let's look at one of the ones we just looked at. 1, 4, 16, 64. We can find the common ratio by taking the term and dividing it by the one in front of it. Like if we take the 16 and divide it by 4, it's 4. We divide it by the one in front of it. If we take 64 and divide it by the 16, because that's the one in front of it, 64 divided by 16, that's also 4. 4 divided by 1, that's also 4. So our ratio is 4. And we just put R. R equals 4. When we had an arithmetic sequence, 1, 4, 7, 10, we subtracted 10 minus 7. And we found a difference of 3. 7 minus 4. 4 minus 1. See, that's why we called that a D, because we found the difference. We subtracted, and when you subtract, you find the difference. When you add, you find a sum, but when you subtract, you find a difference. When you multiply, you find a product, but when you divide, you have a ratio. 16 to 4, 64 to 16. You find a common ratio there. So that's why we're going to use R with geometric sequences. Let me sharpen this pencil again. So they want to give us a little quiz here. Is this geometric sequence 4, 12, 20, 28? Well, if we look at it, let's divide to see if it has a common ratio. 12 divided by 4 is 3. 28 divided by 20, oh, that's not 3. 20 divided by 12, that's, both of those are decimals, 1 point something. This is not a geometric sequence. Actually, this is an arithmetic sequence. If you look at it, it's plus 8, plus 8, plus 8. That's not geometric. 5, 15, 90, 270. Let's see. This is times -3. This is times 6. And then it's times -3. Well, the problem is when we divide 90 by negative 90 by negative 15, we get 6. But when we divide 270 by -9, we get -3. It's not consistent. So it always has to be consistent. 1, 1, 2, 6. Well, that's obviously not geometric because 1 divided by 1 is 1, but 2 divided by 1 is 2. 6 divided by 2 is 3. It's doing something there, plus 0, plus 1, plus 4, but that's not geometric. 7, -70. 700, -7,000. Now look, so if we divide -7,000 by 700, we get -10. If we divide 700 by -70, we get -10. If we divide -70 by 7, we get -10. That's a geometric sequence. So we just test that by dividing. If you see one you don't recognize and you're like, okay, is this a geometric sequence? Well, let's take the last one and divide it by the one before it. 1125 divided by 225. Okay, what's happening? A 5. That's a 5. Okay, let's do the next one. 225 divided by 45. 225 divided by 45. Oh, that's 5. How about 45 divided by 9? 45 divided by 9. Oh, yep, every one of them is a 5. So that's multiplying by 5 every time. That's a geometric sequence. So that's how you can tell. There may be a pattern, but it has to be the same ratio every time. Same ratio. Different forms, just like with the arithmetic sequences. We could have a list of terms. We could have a table. We could have a graph where the first point is 1, 1. The next point's 2, 3. The next point's 3, 9, 4, 27. You know, we could have it in any kind of ways. And remember, it's not continuous. There's no line connecting those because there's not a 1.5 term. There's no value. Between 1 and 2, there's no value because there's no numbers between 1 and 2. You have a 1.1 term. It's either the first term or the second term or the third term. And we don't have a 0 term or a negative term. So again, we're limited on the end to only have counting numbers, 1 and larger. All right. There's 2 different methods for determining the terms of a sequence. Just like there was with arithmetic sequences, we have the same thing with geometric. Recursive requires that we use the previous term in the sequence. Right? Multiply by 4 to get to the next number. Right? When we were looking at the one up here, one of those was multiplying by 5. You know, that was a recursive way to do it. If we have the one before it, we can do it. This one, an explicit formula allows to calculate any term directly where we don't have to know the one before it. So let's take a look, and we're going to build these formulas right here. Deriving the explicit formula. The explicit one's the one we want, where we can jump straight to the 37th term without having to know the 36th term. All right, so at this point, we know how to identify a geometric sequence, and we can find the one after it, right? We just multiply by the common ratio. So if you're asked to find the 11th term of a sequence that goes 2, -6, 18, -54, we take a little bit of calculating to get to the 11th one, right? So let's see if we can find a formula. So let's go through these 4 steps and see what they do. So we know the first term is 2, right? 2, -6 is the second one. So the second term is found by multiplying -3 to the first term. Because we know 2 to -6, we know if we multiply by -3, that'll give us the second term. Then if we multiply by -3 again, that'll get us to the 18, which is the third term. Right? So if we take the second one and multiply by -3, and then if we take the third term and multiply by -3, we get to -54. So we see the common ratio, -3, -3, -3. So using the pattern shown above, where does the 2 originate? Well, the 2 is A sub 1, right? It's the first term in the sequence. Let's check our answer. 2 is the first term in the sequence. All right, where's the negative 3? Well, negative 3 is the common ratio. When you divide a term by the one before that, it's negative 3 every time. That's the common ratio. Negative 3 is the common ratio between each term in the sequence. It can be found by dividing any term by the preceding term. Yes, we saw that. How is the exponent on negative 3 determined? See, because here they said the second term is 2 times negative 3 to the first power, because it's only once have we done that. The third term is 2 times negative 3 squared, because we've taken it times negative 3 here and took it by negative 3 here. We took 2, which was the first term. We multiply it by negative 3 twice. We'll get to the fourth term. We're going to take that first term and multiply it by negative 3 times. That gets us to negative 54. So it's the exponent comes from the position of the term, minus 1. The fourth term has a power of 3. So what's the fifth term? The fifth term would be 2 times negative 3 to the fourth, which would be a positive now, right? When we multiply that times 3, should be what, 162? Yeah, there it is. So let's see if a formula can be found by taking this fifth term and working backwards. So if they take this negative 162, I'll make this big again. So the fifth term is 162.
162.
So that's 2 times 81. And we know the 81. Yeah, 2 is the first term. Is A sub 81 we got by divided by 2, the total. So that is the negative 3 times the fourth power. It's the fifth term. So since R is the common ratio of negative 3, we can substitute that in. 4 is the 5 minus 1. It's the fifth term. So then we know n 5 is n. We can change that to n minus 1. So from that, we have derived a formula we can use. Let me put this up on the screen. A sub n is the first term, all right, times the common ratio. Well, I guess I should put that inside with the ratio. The common ratio to the power of n minus 1. So A is being multiplied by the common ratio raised to the power of n minus 1. If this is the fifth term, we're taking the ratio to the fourth power. Multiply it by the first term. So like in the example above, if we want the fifth term, we can take the first term, which is 1. The ratio, it's being multiplied, we figured the ratio is 4, to the power of n minus 1. 1 times 4 to the fourth power. Well, 4 to the fourth power, it's 4 times 4 times 4 times 4, which is 256. I'm just take it by 1. Using this formula. So let's put this in our notes. Geometric sequence. That look like a C a little bit. Geometric sequence. And this is explicit, right? We can go straight to any term. That's not recursive. We don't have to know A sub 4 in order to find A sub 5. This is the explicit formula. We do have the recursive formula. We can do that one. We have to know the one below it, above it. A sub n is just a sub n minus 1 times r. In this case, if we want a sub 5, we can take a sub 4, which are our formula here, 1, 2, 3, 4, a sub 4, which is 64, and multiply it by our ratio, r, which is 4 to get the 256. We just take a sub 4, which, yeah, that was 4 in this one. So you have the recursive formula and the explicit formula for geometric sequences. You can either take the one before it and multiply it by the common ratio, or you can use the first term and take the ratio to a power of n minus 1. All right. So there is, they have it in our lesson right there. So a sub n equals a sub 1 times r times n minus 1. Well, the variables, a sub n is the position sequence number, the desired term. A sub 1 is the first term, r is the ratio, n is the position of the term in the sequence. So you may be thinking the geometric sequence looks like an exponential function. You're right. This is an exponential function. This is an exponential function. So here they put both formulas side by side, the recursive and the explicit. N minus 1. I put it the other way. I put a sub n minus 1 times r. It doesn't matter. You multiply it, two numbers together. And then a sub 1 times r raised to the power of n minus 1. All right, let's move back up here. Page 4 has the lesson summary. I was talking about the combination of two different parts. If you look at the explicit formula, a1 times r to n minus 1. a1 is a constant, right? That's whatever the first term would be. R to n minus 1 is an exponential expression. So it talks about if you graph it, it would cross. Oh, that's a good thing to look at. It would cross the y-axis at a sub 1. That might be interesting too. Let's go look at that real quick. If we graph this sequence, let's look at the one we were doing, 1, 4, 16, 64. If we said y equals, and let's see, a sub 1, if we use the a sub 1 formula, that'd be 1 times the common ratio was 4 to the power of x minus 1 in this case. Oh, parentheses x minus 1 in that case. There we go. Did that work? It did not cross at 1. What are they saying? A sub 1, horizontal line of y equals a1. Oh, that's if it was just a constant. If you didn't have the r, yeah, it would cross at 1. The constant part is just y equals 1, because that's our first term. But when you have this, graphically, this would be a curve divided by y equals r to the n minus 1. So if we change that to 4 raised to the power of n minus 1, or x minus 1 in this case, to make it graph correctly. Now you get the exponential form of it. So if r is greater than 1, it'll be a growth curve, right? Since r is greater than 1, if this was a negative, it'd be going down because we have decay, basically. So let's look at exponential. Domain and range, again, that's what we're talking about. You can't have a 0th term, a -4 term, all that. So the domain is all integers greater than or equal to 1, and it's only integers. It's not 1.1. It's not 1.5. It's not 1.81. So it says once you have the geometric sequence formula, then you can do that. Identify the 14th term where A1 is this and A8 is this. Okay, let's try that example together. Just because that's a little tricky. If they gave us A1 as 6, and they gave us A8 is negative 468,750. Ooh, that's going to take a calculator, huh? All right, so they gave us this one. And they said, all right, and then what did they want to know? Find our, identify the 14th term. They want to know what A14 is. A14 equals what? So what do we have? We have the first term, we have the 8th term, and they want to know the 14th term. So let's look at our two different formulas. So A sub n on this one, for the 14th term, we'd have to know the 13th term. We don't have that information. If we wanted to use the 8th term, we'd have to know the 7th term. We don't have that information. We do know here, if we use the 8th term, that we know we have the first term, we know what n minus 1 is, that would just leave the r. So let's use this one to figure out what r was. A sub n. A sub 8 equals A sub 1, which is 6, times r to the n minus 1. I'm sorry, 8 minus 1, which is 7. So 6 times r to the 7th. And A sub 8 is negative 468,750 equals 6 r to the 7th. So divide both sides by 6. And that's going to be r to the 7th power. So let's divide it by 6. 468,750 negative. So there's negative 468,750. And let's divide it by 6. So negative 78,125. So we need to take the 7th root of both sides. Since that's r to the 7th, if we take the 7th root, it'll give us r. So let's see, if we do a shift here, we can do to whatever power we want. So if we do this number to the power of 7, we want the 7th root of negative 7825. That's negative 5. So our r is negative 5. If we want to check that, we can take negative 5 and raise it to the 7th power, and we get back to the 78,125. Okay, so now we know r, and we need to know A14. So we can go back to here. A sub 14 equals A1. We know A1 is 6 times r to the n minus 1 times negative 5 n minus 1. N is 14. 6 times negative 5 to the 13th power. Let's bring that calculator back up. 6 times negative 5 raised to the 13th power. Woo, it's a big number, huh? Or actually a very small number because it's negative. 7,324,100. I'm sorry, 218. Have those backwards. 218,750. Let's check how they did and see if we got the same answer. A14, 7, negative 7, 324, 218, 750. That's it. Then they give you another example and the lesson summary. So there's our lesson summary. Geometric sequence formula. Here's the recursive. There's the explicit. So you can print that and put that in your notes. Okay, they give you some practice problems again on page 5. So you can check your work. They'll tell you if you're correct or not. If you do the practice problems in the lesson, which I always recommend, find the 10th term of this sequence, 2, 8, 32. Find the 10th term, submit. It's got 5 practice problems for you. All right, let's go to the assignment that does count. Those practice problems don't count, but they certainly let you know if you know what you're doing. See what we have. Find the 16th term when you have the first term and the 8th term. We did a problem just like that. That was the last problem we did. Which one of those is that? Find the 17th term when you have the first term and the 5th term. And the 5th term is a decimal, 150.06. Round the common ratio and the 17th term to the nearest hundredth. That's 2 decimal points. Notice the answers over here are 2 decimal points, 0.31, 0.05. So you're going to round that. They're going to do a tough one for you. All right, a bacteria culture begins with 15 bacteria, which doubles. Well, you know what your ratio is if it doubles. How many are there during the 12th hour? Hint, R equals 2. Ratio, double. Okay, given the functions f of n equals 500 and g of n equals 9/10 n minus 1, combine them. Would you subtract, subtract, add, multiply, or what are they doing there? Oh, they're multiplying the 500 times the 9/10 inside the parentheses. Okay, so which one of those would it be, and which one is the 11th term? And 5th problem, they give you a table. The first term is -4, the second term is 20, third term is -100. What is the formula and the restrictions to the domain? And again, if you know the restrictions to the domain, already you can throw out 2 of those. So which one of those would be the formula? All right. That's it, guys. That's our 2 lessons for the week. Arithmetic series, geometric sequences. So that gives you a good idea what geometric series is going to be next week, right? It's going to learn to add all that sequence up that multiplies with the common ratio. So, all right, any questions on that? I'll give you guys the rest of the hour to you can start your math. I won't keep you in class. You can have some time to work on that because we're done with this week's lesson, and I will catch you guys next week. I'm still hopefully have last week's. We had a very, very short week, so I don't have last week's video posted yet, but I'll get that posted right away and try to get this one posted too. So, all right, guys, have a great week.